All right, so welcome to my talk, and this is going to be on the topic of internet voting and the challenges that can happen with this. So this is the collaboration with University of Karlsruhe Institute of Technology in Germany, and I am from the IT University in Copenhagen, Denmark. So internet voting, it has been widely discussed, especially during the pandemic, and it has in fact been used in several countries for political legally binding elections. So this is not new. And despite the several advantages of internet voting, of course, it has security concerns. And one of the biggest one is the fact that there is a potentially insecure voting client. So the assumption is the voters use their personal devices, their laptops, their smartphones. And what can happen, for example, if the attacker manages to infiltrate this device, for example, by installing the malware on voters' laptop. Two things can happen in this example. First of all, assuming the voter goes to the election website and selects their choice, party A, the attacker might know that the voter has voted for party A. And what the attacker else can do is that they can just modify their vote from party A to the vote for party B. So unless there are specific ways for the voters to verify that indeed the right vote has been submitted to the voting system, the vote will be manipulated without the voters knowing. So this is the biggest challenge in internet voting, and it has indeed been addressed quite extensively in the election security community. In particular, one of the proposals to solve this problem, or at least to mitigate these risks, would be return code-based verifiability. Now, the way it works, and this is a very simplified description, is that before the election, the voters get the paper code sheets, where each voting option, in this case party A and party B, are assigned a specific voting code. So this voting return code. So these return codes are unique to the voter and to the voting option. The assumption is they're secret and only the voters know these codes. So what the voter does, the voter goes to the election website, chooses their choice, party A. The vote is transferred to the election system, and the election system outputs the return code. So in this case, the voting device or the voting website outputs the return code as well, and the voters can check, yes, though this code 6439 is indeed the code that is on party A, which means that the vote for party A has been recorded on my behalf. So in this case, even if the attacker manages to infect the voting device, there is no way they're going to know the valid return code unless they actually submit the vote for party A that the voter has intended. So at this point, one might say that the problem with vote integrity in presence of malicious voting device has kind of been solved, at least to some extent. And indeed, this approach relies on the voters being able to detect manipulations, and it has been used in elections in Switzerland, for example. So this is tested in practice. Now, still one problem remains, and this is the problem with the vote secrecy, because once again, if the attacker somehow controls the voting device, it is possible that they still will be able to find out that the voter has voted for party A. And the solution for this has also been proposed, and the so-called verifiable code voting. And again, this is not new. This has been proposed in the literature since 20 years. The idea is as follows. Again, a very simplified description. Before the election, the voter gets, again, the code sheets with return codes, as explained before, but now the voter also has the so-called voting codes for each voting option. Again, the assumption is these codes are secret and known only to the voter. And what the voter does when they vote to vote for party A, they, instead of entering just this option in plain text, they enter their corresponding code. The code gets transferred to the voting system, and the voting system outputs the return code as before, so that the voter can compare that indeed this return code corresponds to party A. So in this case, if this actually works in practice, then vote integrity is solved, and of course under the assumption that the codes are secret. And the vote secrecy problem is also solved because the attacker only sees the code that has been transferred, but not the actual voting option. So again, this solution is not new. It has been known and discussed and iterated over 20 years. However, it has not been used for actual real-world elections. And one of the concerns is the usability. So would the voters actually be able to use the voting system if they have to enter codes instead of just choosing their voting option? And this is the problem we attempted to solve in our work. In particular, we made the following proposal, how to make this verifiable code voting more usable. And what we propose is that instead of the voters entering their codes manually, they rely on QR codes. And how it can look like is that before the election, the voters get voting cards, one voting card per each option. On the front side of the voting card, there is the QR code encoding the voting code. And on the back side, there is the voting option in plain text and the return code. in order to vote, the voter uses some device, such as smartphone or other device that is capable of scanning QR codes. The voter scans the QR code of their chosen voting card. The voting device transfers the corresponding code to the voting system, and the voting system returns the return code, which the voters can then verify. So this is, in a nutshell, our proposal. Again, very simplified. If you look at the paper, you see it's more complicated than this, but this is the main idea. And if it actually works, then again, we have the advantage of vote integrity and vote secrecy being protected. And given this proposal, the research questions we focused on in our work is, first of all, is it actually usable? So we wanted to get some idea of what the system usability score for this proposal is. And then we actually wanted to see whether the voters are able to detect manipulations of their vote using this system. And the topic of manipulation can be tricky, and the type of manipulation we looked in our work is as follows. So imagine there is indeed an attacker controlling the voter's smartphone, which they use to vote. The voter votes according to the procedure I described above. They scan the QR code on the corresponding voting card. What the attacker can do, assuming the attacker wants to just block the votes. So they want to make sure that this vote of this particular voter does not get included in the tally. So the attacker does not forward the vote to the voting system. Now the attacker, of course, has a problem that they don't have the right return code. So what can they do? They can do as follows. They can manipulate the interfaces of the voting client, or for example, of the election website, because, as you recall, the assumption is they control the voting client. And what they can do is that instead of outputting the return code, which they don't have, they output some generic message like, "Thank you for your vote, you're now done." And the attacker can hope that if the voter is not very familiar with the verification procedure, the voter will think, okay, they're done, and not do anything else and not raise any alarms. So the attacker would succeed manipulating the vote without actually knowing the return codes. So vote secrecy still remains intact, because still the attacker only sees the codes, but integrity might be violated if the voters don't notice this kind of manipulation. So the question we wanted to answer is, how dangerous is this? Will the voters be actually able to detect that something goes wrong in this case? And in order to conduct this, we have done an online study, which had two groups. One group of participants interacted with a mock-up of this voting system without any kind of manipulations. So the purpose was to see how usable the system under normal conditions is. And the second group was subjected to simulated manipulations, as described before. So the purpose was to see whether they detected or not. So the study design was as follows. Before the study, the voters have received materials via postal service. So we conducted the study during COVID, and which is why we could not invite them into our lab, so we had to conduct the study remotely. So we sent them the materials before the study, and they were asked to read the materials, which concluded of general instructions, information about the study, of the roll call, telling them that they are the voter in this election, and they intend to vote for this particular option. And it also included voting materials, including voting cards and some other materials that are relevant for the election. So after doing this, the voters were instructed to cast their vote according to their roll call and using the mock-up of the system we developed. And depending on whether the voters were subjected to manipulation or not, the rest procedure was as follows. If the participants were in a group without manipulation, then after completing the vote casting, they were forwarded to the survey, where they were asked a questionnaire from the system usability scale and some other feedback about the system. If the voters were indeed subjected to the manipulation, they had two options. So on the voting materials, we had support number. And we told so the materials would say the voter, if you experience any problems, call this number and tell us what this is. So this number actually belonged to the person who has conducted the study, so that participants could actually call the number. So the manipulation was introduced, and if the participant has called this number, so they have reported the manipulation, if they did not call this number, if they did not report the manipulation, they were forwarded to the debriefing survey, and so they were told that indeed there was a manipulation and asked some questions about their experience with the system. If the voters had called this number, they were debriefed on the phone, so they were told that actually this manipulation is deliberate, that they have noticed, and then were once again forwarded to the final survey with questions about their experience with the system. So our results were as follows. 65 participants interacted with the system with or without manipulations, and these were the results. So the usability score was kind of high, 82 out of 100, which is usually considered very good. So at least we could kind of hope that the system is indeed usable, the manipulation detection was not that great. So only 41% of the participants were actually able to detect manipulation. Now, this does not look great indeed. However, when we look at similar studies that also look at systems with similar mechanisms for verification, we see that they don't really perform any better. So for example, the studies done with the original Swiss post system only had 10% of participants detecting such kind of manipulations, and in a modification of the Swisspot system, 43 participants did it. So at least our proposal did not do much worse, or did not do worse than the proposal from previous work. Yet it still has an advantage of security because our proposal utilizes verifiable code voting. So under the assumption that voting devices can be compromised, still vote integrity and vote secrecy is protected, while with the two other evaluated systems, only vote integrity will be protected, but if the voting device is compromised, then vote secrecy can also be compromised. Right, so to summarize, we have proposed system for verifiable code voting, and we have shown that it can indeed be usable. What we still can work on is to further improve the manipulation detection rate, because still, as you see, 40% being able to detect manipulation is not great, so maybe something can be done to improve this. And another direction of future work is to focus on systematically testing for these manipulations, because we came up with one way the attacker can modify the voter interfaces to see if it works or not, but maybe there are more systematic ways to come up with all kind of different ways that the attackers can do to kind of deceive the voters into not completing the verification procedure. All right, so this was it. Again, I'm presenting here only a part of what we have done in this work, so if you're interested to know more, please read the paper and please come talk to me in the breaks. And for now, thank you for your attention. I'm happy to hear questions.